All right, let's look at how to do a quick Revolute join inside LS-Dyna. Gonna be a very simple video. Um, what I'm trying to do is actually create a series of all of the joins in Dyna one by one, and this one is a very simple one. So this is a basic Revolute join from the documentations. It only requires 4 points in space to be defined. Point 12 is in the center of the first cylinder, and point 34 is the center of the second cylinder. And all we have to do is to make sure they're aligned on the same coordinates, same axis of the rotations, and that's all you really need to do. This is the keyword I'm going to be using. Basically, you only require 4 points, like we previously defined, right? And this is an illustration of how those 4 points are basically being located. So if you scope to the cylinder on the first one and the second one, you basically maintain that they only have the rotation axis, and this is what happens with the revolute joint. You can actually apply a load on the bottom beam, right? It will basically act like a cantilever beam, and over here you have a rotation that happens. That's a very, very convenient way to do a revolute joint that also allow deformation to occur on one of the beams. And let's do a quick example problem to demonstrate how to do this, right? So what I have here are the two different beams. What I'm going to do here is that I'm going to basically create two coordinate systems. The first one, I'm going to scope to here, and notice how once I do that, I have these 3 points not being defined, right? And then next, when I'm going to do the same thing, I'm going to create another coordinate system, and I'm going to put it in the second one. And notice how these two have the same x-axis. I'm sorry, have the same y and z axis, only the x-axis is different. And that tells me that they're basically located on the same rotation axis, which is the x-axis you see here. Now the coordinates of these three coordinates right here are what I'm going to use for point 1, 2, and point 3 and 4. Now in terms of the meshing, it's pretty trivial in this case. I'm just going to do say what 2 to negative 3, which is like 20 millimeters, and then I'm going to assign a multi-zone to both of these, which hopefully is going to generate a grid mesh for me without me having to do anything else. So let's go ahead and try that. Okay, good. And then I'm going to get rid of the contact because I don't need any contact here. We're going to set the termination time to say 0.1 second for something like this. It's mostly just having some termination time. Now, the actual, we're going to set, say, for example, this here. We're going to set it as a fixed support, which is an MPC fixed support here. And then we're going to apply a remote displacement, which is going to be basically acting here. Okay, good. Turning down the music a little bit. All right, so this is going to be where my remote displacement is going to be. What I want to do here is that actually that's not what I wanted to do. I want to put it here. Put it here. Okay, this is where my remote displacement is going to be. Now what I'm going to do here is I'm going to move this thing across the negative x-axis by a little bit. I'm going to do like negative e1 to negative 3, about 10 millimeters. Right, so he's going to rotate, gonna go upwards. What I also want to do is rotate this relative to the x-axis by a little bit, and then the coordinate I'm going to choose for the x-axis is actually going to be this one, right? So I'm going to rotate this by the x-axis also a little bit. So the way I'm going to do that is I'm going to do this by negative 45 degrees. And then I want to make sure this thing is located properly here. Okay, you see how now this is going to go upward this way as I'm going to rotate by the axis by a little bit. I want to set this to rigid. Okay, and this is basically a CNRB. We're going to do a boundary prescribed notion rigid, which is going to apply to that node right there, and it's going to be what generates that rotation and translations. And lastly, we're going to generate a joint. Now, the joint what I usually do is I actually have a keyword prepared in my own repository. So in this case, I'm just going to copy it, and I'll explain what I did as I copy these. Now notice a few things, right? So these two constraint nodal rigid body, first of all, he's going to call out a node set of 9001 and 9002. That's something we have not created. So what we want to do right now is create node set 1. I'm going to create a node set 2 right here. Now see the node set 1, node set 2, I'm gonna generate a nodal selection from each of these, right? I'm gonna call this 9001. I'm gonna call this 9002. Right, so notice 9001 is a set of node, 9002 is a set of node. And what I'm gonna do is that I'm gonna put them into a constraint nodal rigid body, which means these two set of nodes are gonna become rigid, and they're gonna be assigned a CNRB ID of 8001. The ID of 8001, 8002 is what I'm gonna constrain together with a joint. Now you see this constraint joint coordinate revolute, right, is basically constraining these two nodes together such that they only have a relative rotational degree of freedom. And because we do that, because we're doing that because we're doing that revolute joint, we're going to require 4 points in space. This 4 point in space is what we're going to use. Sorry about that. The 4 point in space is going to be what we use to constrain it together, such I generate that revolute joint. And notice how these 4 points right here are corresponding to in here, right? So this units here is a little bit off. I'm gonna change the unit system to millimeter, Newton millimeter ton, and which is what I'm gonna export this thing to. And you notice how here is negative 5.25, 12.7, negative 12.7, and 3.175, 12.7, negative 12.7. That corresponds to these coordinates right here, right? Which means the first 2 points are going to be coincident, represents here, and the second 2 points are going to be coincident, which is going to represent here. And together, this is going to generate that revolute joint, right? I'm doing that inside a keyword because if you think about it, it's actually really, really easy to do. You can try to do this thing where you have the same functionality as the mechanical thing, right? You can try to do it here. In my opinion, right, I've seen buggy behavior with this functionality so far, and even if it's not buggy, it's arguable which is easier. In my opinion, this is far easier in my mind because I can read this text file and know exactly what I'm looking at, right? And that's actually a way easier way to set up a Dyna model than using these objects, which are buggy at best right now. And that's really all we have to do. And then once you basically write out the input file and solve it, right, it's going to basically generate a response that look like this. And this is how you do a revolute joint inside LS-Dyna. All right, thank you.